Think about your choice of vehicle for a moment, associates. If you're driving through smooth coastal highways, a high-end electric sedan is a dream. In the world of mass spectrometry, electrospray ionization, or ESI, is that sedan. It's the gold standard for polar biomolecules, but it's notoriously sensitive. It demands clean samples and low flow rates. But what happens when the pavement ends and you hit the mud and gravel of the analytical wilderness? What if you're dealing with nonpolar compounds that ESI simply can't grip? Or a dirty environmental extract full of interferences? Welcome to Module 5.4, Bridging the Gap. Today we meet the rugged 4x4 off-roader, atmospheric pressure chemical ionization, or APCI. We're building your strategic map for the nonpolar world. Before we dive into the hardware, we must understand why we need this bridge at all. Standard techniques like electron ionization live in a high vacuum. However, your liquid chromatography system is pushing liquid at a continuous flow. If you spray that liquid directly into a high vacuum source, the vacuum will collapse instantly. Furthermore, many analytes have a personality conflict with vacuum sources because they are thermally unstable and break apart when heated under vacuum. We needed a way to ionize samples at atmospheric pressure before they ever entered the mass analyzer. This necessity birthed atmospheric pressure ionization. We aren't just moving from gas to ions anymore. We are moving a rushing liquid stream into a charged gas phase without losing data integrity. Our mission today is to turn you into an ionization architect. We are building a decision matrix for the lab. By the end of this module, you will master the two unsung heroes, APCI and APPI. We will start with a hardware audit of the APCI source, seeing how the heated nebulizer and the corona needle act as the engine and spark plug. Then, we'll move to the selective world of APPI, where high-energy photons take the place of electrical discharge. Crucially, we'll focus on the ROI of cleanliness and why these techniques are so much more tolerant of salts and dirty samples. If you've ever had your source crash because of salt buildup, this session is for you. Let's look under the hood of an APCI source. If ESI is about droplet physics, APCI is purely about gas phase chemistry. The first component is the heated nebulizer. Imagine a high-tech spray paint gun. Your liquid eluent meets a stream of high-pressure nitrogen gas that nebulizes it into a fine mist. The probe is heavily heated, often between 350 to 500 degrees Celsius. This flash vaporizes the solvent and the analyte instantly. By the end of the probe, your sample is a hot, dense gas cloud. Because of this, APCI can handle the full fire hose of a standard HPLC up to 2 milliliters per minute without breaking a sweat. It is the ultimate tool for high-throughput screening. At the center of the APCI source sits a sharp, stainless steel needle called the corona needle. This is the spark plug of your mass spectrometer. We apply a high voltage, typically 3,000 to 6,000 volts, to create a localized plasma of high-energy electrons. Notice the subtlety here. The discharge does not hit your analyte molecules directly. Instead, the spark hits the nitrogen sheath gas and vaporized solvent molecules, which are in much higher concentration. The formula is S plus an electron produces the radical cation, S plus dot, and 2 electrons. This relay race charges the solvent, which then carries that charge to the analyte. This chemical negotiation happens at 760 torr. Once reagent ions are formed, we enter the atmospheric ion molecule dance. Because we are at 760 torr, molecules are packed tight and bumping into each other billions of times per second. This makes APCI incredibly efficient, essentially chemical ionization on steroids. The reagent ions act as middlemen through two primary pathways. First, proton transfer SH++M produces S and MH+. This soft path gives you the molecular weight conformation. Second, charge exchange S plus dot plus M produces S and M plus dot. This gas phase flexibility allows APCI to ionize those stubborn nonpolar molecules that ESI simply cannot touch. Don't ignore the drying gas, the silent partner that keeps your data professional. This stream of nitrogen flows in the opposite direction of the ions, like a protective wind. Its job is to facilitate ion desolvation by stripping away the last few neutral solvent molecules. Without this gas, your ions would enter the mass analyzer wet, causing baseline drift and noise. Furthermore, the drying gas pushes away neutral particulates and salts, while the charged ions are pulled in by the electric field. If your peaks get smaller over a long run, check your drying gas flow. It is the key to maintaining a clean system and ensuring only naked ions reach the detector. But what if your analyte is so non-polar, like a neutral lipid, that it refuses to accept a proton? Even APCI might fail here. Enter APPI, atmospheric pressure photoionization. In this mode, we trade the lightning bolt of the corona needle for a vacuum ultraviolet lamp. This lamp, filled with krypton or argon, shoots high-energy photons into the vapor stream. We call this the photonic matchmaker. We aren't using electricity, we are using pure light. This technique is incredibly selective for aromatic compounds and highly nonpolar species. When the social dance of APCI doesn't produce a signal, reach for APPI. It is a cleaner, more targeted way to give your molecules the spark they need. Here's the clever bit: the selection of ionization energy, or IE. We typically choose a lamp energy, like 10.0 electron volts for a krypton lamp, that sits in a strategic window. Notice that common solvents like acetone nitrile have an IE of 12.2 electron volts, and methanol is at 10.8. This means the 10 electron volt photons cannot ionize the solvent. The light simply ignores the mobile phase. However, most organic analytes have IE values between 7 and 10 electron volts. This allows the photons to smack the analyte directly into an ionic state, M+, while leaving the background invisible. This results in cleaner baselines and higher sensitivity for difficult targets. Sometimes, even with the lamp, the analyte won't play ball. In these cases, strategists use a dopant, like toluene. Think of the dopant as a professional matchmaker. We add it to the mobile phase in high concentrations. The lamp ionizes the dopant easily because it has a favorable IE. The formula is D plus a photon produces the radical cation D plus dot and an electron. Now you have a high concentration of charged dopant ions that seek out your analyte and finish the job via charge transfer or proton transfer. This dopant-assisted APPI is a game changer for sensitivity, combining the selectivity of light with the efficiency of chemical ionization. So how do you choose? Here is your consultant's cheat sheet. APCI is your gold standard workhorse, excellent for semipolar to nonpolar small molecules up to 1500 Daltons. If you have a standard pharmaceutical mix, APCI is your first choice. However, APPI is your specialist for very low polarity compounds or dirty matrices. APCI is moderately susceptible to ion suppression because the discharge is less discriminating. APPI, however, has very low ion suppression because photons are more selective. For nonpolar lipids, APPI can be 2 to 4 times more sensitive than APCI. Both are far more salt tolerant than ESI. Let's wrap up. Remember the golden rule for your lab. If it's polar and big, use the ESI electric sedan. If it's moderately polar and small, go with the APCI 4x4. But if it's non-polar or your matrix is so dirty that your baseline looks like a mountain range, APPI is your ace in the hole. APCI is where gas phase chemistry meets LC convenience. APPI is where the power of light unlocks the invisible. You are now an ionization architect who knows how to bridge the gap. Next time, we enter the bio gateway, exploring how electrospray ionization made it possible to weigh massive proteins as easily as salt. I'll see you at the source.